is the problem of the rainbow antimagic coloring. Here the problem to determine the rainbow antimagic connection number for any graph is considered to be harder problem. Suppose we are given an H antimagic vertex graph. How are we convince whether the H antimagic graph is a rainbow connected with a minimal rainbow antimagic connection number or not? Of course, it is very hard. If the order of a graph is constant, then this problem become easy. However, if the order of the graph is unbounded, then the problem falls into NP problem. So normally in rainbow antimagic coloring study, we propose at least 4 questions. The first question is, what is the sharpest lower and upper bound of the rainbow antimagic connection number? Later, I will send you some article, some paper which are already published, which has been published. Then you will find out the sharpest lower bound. Yeah. And the second problem, what is the exact value of the rainbow antimagic connection number of special graph? So for student, I believe we can start from the finding the exact value of the rainbow antimagic connection number of special graph. So it is very important for exercise. And then the third problem, can we characterize the rainbow antimagic connection number? It is a little bit harder than only finding the exact value of the specific family of graph. And the last one, the hardest one is, can we construct a rainbow antimagic coloring of graph by using smaller rainbow coloring of H antimagic labeling? That's the problem, yeah, so far. Okay, a strategy how to solve the problem. Yeah, normally strategy 1, consider the complexity of the constraint, maximum degree of vertices. Since the level of vertices adjacent to a vertex whose degree is the largest are distinct, their H weight must be distinct. So that's why in our paper, in my paper, already stated about the sharpest lower bound. The sharpest lower bound is a maximum rainbow connection number and largest degree of a graph. That is the sharpest lower bound. Yeah. So that's why when we need to find out the rainbow antimagic coloring, then first we should establish the rainbow coloring itself, because the sharpest lower bound is a combination of maximum degree and the rainbow connection number itself. So the lower bound is the maximum of those number. Secondly, analyze the existence of the rainbow antimagic labeling based on the existing of rainbow connected graph. And the third one, use the previous relevant preposition, lemma's theorem, and so on. And strategy 4 is consider the existence of rainbow connected graph. Let me show you some example first before we continue about this. Yeah, okay. I use a different device. Yeah. Let me show you something. Yeah. Screen. Okay, start. Yeah, sorry, I just okay. Yeah. Let me show you some things. Step by step, of course. Yeah. Can you see this one? Yeah. Let me give you some example. Yeah. Just a minute. I don't know how to clear this one. Yeah. Okay. New one. Okay. Yeah. Okay. For example, we have graph path. Ya, sebentar saya akan mencoba untuk menghapus ya. Oke, let ya. Oke. Ya. Let me give you an example. Ya, oke. So, first of all, yang pertama kita bicara rainbow. Ya, rainbow coloring. Apabila kita memiliki path, ya, oke. Then rainbow coloring, we start assigning label, assigning color from the each element of a graph. Yeah, that's rainbow coloring. Yeah, but for anti-magic labeling, yeah, we assign label on each vertex. For example, 2, 3, 4, 5. So look at here. We have 5. We have 6, 7, 8. Yeah. That's anti-magic labeling. Yeah. Now, what about air? Yeah. AC, rainbow anti-magic labeling. For rainbow anti-magic labeling, we can have 1, 2, 3, 4, 5. Yeah. For example, here we have 6, 7, 6, 7. Boleh saya bertanya dulu, yang rainbow coloring 1, 2, 3, 4 dalam satu path. Berarti this guy, these graphs already show the existence of rainbow path. Yesterday we already talked about rainbow path. Rainbow path, if you want to go from U to V, yeah, then all this one must be different. Yeah, understand?
Yes, Pak.
Then anti-magic labeling, you assign label, whatever the way you assign label is okay, such that the edge weight of every two adjacent vertices must be different. Look at here, 1, 2, 3, and then we start 4, be followed by 4, and we have 5. Then we consider the edge weight 5, 6, 7, 8. So this is the edge weight, yeah, of the graph is 5, 6, 7, 8. It is all different. Yeah. And this, we consider this as a anti-magic labeling. Now, from both notion, we combine the definition. So before we have a rainbow coloring, we should assign label first on the every vertex, 1, 2, 3. Now we do not put 4 here, but we start 4 here, 4 and 5. My question to a student, yeah, does this graph admit a rainbow anti-magic coloring? Apakah graf ini memiliki sifat daripada rainbow anti-magic coloring?
The last graph, is it, Prof? Is it the last graph? Is it the last graph, Prof?
Yeah, yeah, the last one, this one, the last one, the last one.
Supposedly, it's satisfied, the condition.
The condition is not satisfied?
Satisfied, I think
No,
it's not satisfied because
not satisfied, because if you want to go from this one here, UV, and then you have 6, 7, 6, 7. Nah, there is a repetition. Yeah, itu ada repetition. Understand?
Okay.
Yeah, so it is what contradiction with the definition, then it is not satisfied. Yeah. So this graph does not admit a rainbow anti-magic coloring. Can you make it how to have a rainbow anti-magic coloring? Can you?
With past 5 and Prof.
Yeah, again the same.
Oh.
Yeah, okay. Okay, can you make it such that they admit a rainbow anti-magic coloring? Ayo, siapa yang bisa melabeli sedemikian hingga dia menjadi rainbow anti-magic coloring? Ya, ya tunjukkan ke saya, bisa berupa kertas atau apa, sehingga bisa didekatkan dengan itu. Coba. Bisa, coba.
1, 2, 3, 4, 5, 6, 7. 1, 2, 3. plus 5,
Yeah.
6, 7, 5, 6, 7, 8, 10, 13. Oh, done.
Okay, great. You got it. Please show me. Can you show in the screen or whatever?
How to share? Masuk.
How do you say? You have
Pilih cuba aduh. Pusing. Apa dia? Pusing. Tunjuk ke kamera. Manually.
yeah, no, nah, good. Just a minute. 1, 2, 1, 2, 3, 4, 5, 6, 7. And then you have 4, 8, 12, 13, 15, 6. Yes, great. Very good. Yeah. Yeah, that's yeah. Very good. Yeah. Okay, that's a rainbow anti-magic coloring. Yeah. Okay. Let me show you again. Now. Yeah. Now the problem now, when you got that label, and the next question is, does the label form a pattern? That's the next question. Does the label form a pattern? Apakah label yang dituliskan dalam graf itu membentuk pola? Yeah. If it is yes, then by pattern recognition, we can extend the graph of larger order of a graph. So if, for example, here, if I can say here, 1, yeah, okay, 1, and then 2, sorry, yeah. Just a minute.
Okay.
1, yeah. 2, 3, 4, yeah. And then I have 5, 6, 7. Then I can get 6, 7, 8, 9, 10, 11. Yeah, all different, all distinct. Then it is guaranteed to have an existence of the rainbow path. But not only that, we need to make sure that the labels form a pattern. Look at the pattern here. When I have got this pattern, 1, and then got 2, yeah, 3. So what do you say about this pattern? Every vertex, yeah, jump, yeah. Alternately jump, yeah, understand, yeah. Okay, and then again, we start with the following vertex of the first vertex, and then again jump, yeah. So then you can do whatever you like, the order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, no problem. Since you already know the pattern. So how do you assign the label? 1, 2, yeah, 3, 4, 5, 6, 7. Again from here, 8, 9, 10, 11, 12, 13. It is guaranteed you will have a distinct H weight for all rainbow paths. 9, yeah, 10, 11, 20, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, that's it. So, Sharifa, your student already saw me the picture. Can she extend the order? Can she extend the order? The larger order, then these labels still what valid for the larger order. Can you extend? Yeah. Yeah, that the principle of studying the rainbow anti-magic coloring. So actually, it is also holding for the any type of graph labeling study and also coloring study as well. We need to perform the pattern. Yeah. Otherwise, it is very hard to extend. Yes, silakan.
I want to ask, because the first example that you give us is the odd vertices. So for us to extend the previous graph, so we need to choose the odd vertices also. Is it correct? Meaning,
did you say odd and even? Yeah. Yeah, understand. Yeah. Sometimes it is not satisfying for even number of pieces.
True.
Yeah, but it is satisfied for odd number of vertices. Then our theorem that we can try to prove only for a specific condition, that's mean for order of n where n is odd. So what about for even? Then we can find another pattern again for even order of a graph. Sometimes that there are two cases. Sometimes, yeah, even and it's different. But I'm not sure if you have. But I'm thinking if it is you have a different pattern how to assign. For example, yeah, sorry. For example, this one. Okay. And then I get 1, 2, 3, 4, 5. Yeah. This one is 3. Okay. Sorry. Yeah. This one is 3, 3, 5, 7, 9. That's okay. That's also satisfy for even order of a graph as well. Coba, punya saya charger. Yeah. Just a minute. I
Okay.
Udah pandai. Dia lipo.
Yeah. Okay. Yeah. Look at that. Yeah. Okay. Can you have it? Yeah. Ya, sudah. Ya. Gimana, Syarifah? Yeah. So with this case, then any order of a graph will be satisfied, no problem. So need to think about how to label. Yeah, how to label. Then we can extend. We can extend whatever the order. Yeah. Whatever the order. Okay. No problem. Then you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Then 3. Yeah. And then 5, 7, 9, 11, 13. So actually, this form an arithmetic sequence of different 2. Yeah. Understand? 3, 5, 5, 7, 7, 9. The difference is 2. And the initial number is 3. And whatever. So you can extend. That's the rainbow part. Understand? Yeah. Okay. So this is very easiest because it is just a part. But if it is different, not a part, then it will be complex. Yeah, because and the application also we already studied and I already published in the paper. Any tree, yeah, also having these properties. What is the properties? If you count the number of colors, how many different colors does part have for having a rainbow anti-magic coloring? How many colors? How many colors? Yeah. How many colors?
What the question? From what the question?
Yeah. The question is, if you count this one, the red one,
The red one.
for this one, the red one shows the colors of rainbow anti-magic coloring. Colors mean in the proper coloring is the number of difference HUIT. For example, here 6, 7, 8, 9, 10, 11.
And -1.
If we show in the H set, then my question is actually, what is the cardinality of HUIT? That's my question.
And
The cardinality.
1, 2, 3, 4, 5, 6. And
What is the cardinality? Yeah?
And -1. Is it correct, Prof?
Yeah.
And -1.
Yeah. So for any vertices, any tree, so actually we have that's colors n minus 1. Yeah. So if the order of n, then the number of colors of the rainbow anti-magic coloring is n minus -1. Understand? Yeah. So, okay. Do you have any question? Do you have any question? Yeah. So we are starting from the easiest one. Yeah. But if you say it is too easy, then you should raise your hand. I can go for further description then. Yeah. Okay. Any question?
No.
Yeah. Okay. Let me show you now. Now, how to have how to start to proving logically according to inductive or deductive concept of mathematics. And normally, when we try to have this graph, okay, so whatever here, for example, I try to have 1, 2, 3, 4, yeah, 5, 6, okay. Then we have to have a notation of every vertex. The notation of every vertex. Then x3, x4, x5, x6. Yeah. Of course, etc. Because number of vertices of path could be n. Then try to have a counting process of the cardinality. The cardinality, first of all, is vertex set. And then I say vertex set is xy for y up to n. Yeah. And then the cardinality of v, of course, is n. Yeah. And then what about h?
N minus 1.
H is xi plus 1. Am I right?
True. True. True.
Yeah, but what is the domain of I?
I n minus.
Yeah, n minus 1. Yeah, of course. Otherwise, we have extra vertex if we say until n. Yeah. Understand? Yeah.
True.
So what do you think? What is H? Cardinality?
N minus 1.
Yeah, n minus 1. Need to have this calculation first before we establish or develop an algorithm or a bijection function. Yeah. Sorry, injection function. Yeah. Then we have here 3, 5, 7, 9, 11. Yeah. Let me show you. Yeah, from the very simplest one. Yeah. So have you made the notes? Have you made the notes?
Yeah, then the prof.
Okay, okay. Yeah. So Sharifa,
Yeah.
a student sitting next to you, is he a postgraduate student or undergraduate student?
Master student.
Oh, very good. All of them master student. Yeah.
No, just Aisha, master student. And online we have Ayu. Ayu is PhD student.
Ah, okay, okay. Very good, very good. Yeah. So it will be very nice if we can have a joint research, or you can ask your student to do this research, and then I will supervise them with you, of course. Then very nice. Yeah.
And Graphic, another 3 students from FIT, undergraduate student.
Or for machine learning, you mean?
No.
No. Oh,
In this class now.
okay, okay. No problem. So we are supervising students from undergraduate until PhD level in our university. So we are talking the same thing about graph, and we are starting the same thing. We start with the simplest one. Yeah. And after that, they can do individual. Okay. Let me show you again. Yeah. From this one. Yeah. Okay. when we have this representation, yeah, 1, 2, 3, 4, 5, 6. Of course, then we have x1, x2, x3, x4 until xn. Now we can develop a function in such way whenever people asking about the labels of a certain vertices, then we just use that function, and then finally we can get the answer. With this guy, with this pattern, of course, the label, yeah, okay, the bijection, yeah, is fxi is equal I for I n. Am I right? Yeah. What is f? F is a function of a label of vertices. Yeah. Because so if I equal 100, then you have x 100. What is the label? Of course, 100. Yeah. Understand? Yeah. Now, what about this one? 3, 4, 5. Sorry. 5, 7, 9, 11. Now you are asked about a bijection of ages. Actually, they're the same with age weight. Yeah. So what is the bijection? xi plus 1. Look at that. We have 3, 5, 7, 9, 10. 3 is actually arithmetic sequence. Yeah. 3 is an initial value. The difference is 2. Then we have an arithmetic sequence a plus n minus 1. B is the different. A is the 3 plus n. We already say n as a representative of I. Then we can say I. And D is different too. Then we say 2i plus 1. That is the bijection of xi plus 1. 4. This one is I minus 1. What do you think?
Try. Correct.
Understand, yeah? So whatever you are asked, for example, what is the age weight of, ya, ini pertanyaannya, misalkan, ya, what is the age weight of 1,000?
1,000.
What? Yeah. Understand? So then you say I is 1,000. So when we have 1,000, 1,001, then 2 times 1,000. Yeah. plus 1. So you have 2000. Understand? Yeah. That's the H weight on X thousands, X 1001 as an H weight. Ya. Nah, sampai di sini adakah pertanyaan? Bagaimana membangun fungsi? How to develop a bijection?
No problem. There is no question.
Okay, very good. Yeah. So from this one, we can conclude that the rainbow, yeah, connection, antimagic connection number, the rainbow antimagic connection number, RAC of PET, you can say n-1. Yeah. So, how to put in the lemma or theorem, how to write the lemma or theorem of this case, then the lemma or theorem, you can see, have you made the notes for this one?
Yes.
Yes. So the theorem then, theorem, for example, yeah, theorem, theorem 1, yeah, and let Pn be a path of order and RAC of path and is equal -1. That's the theorem here. So you already have one theorem that you can publish. Yeah. But it's already done. It's already done. Yeah. Understand?
Thing proving from.
Yeah. Proof this theorem. So if some people ask, you are studying rainbow antimagic, how do you study rainbow, inductively or deductively? Actually, we are using a deductive approach. The process that beginning we told you, actually that only a process of finding the rainbow antimagic coloring. So actually the real process of that, if you develop a theorem, then you should start deductively about the theorem. Yeah. What is deductively? Means we should have a lower bound and we should find out the upper bound, lower and upper.
Sure.
Then you compare together. If it is exactly the same, then you got it. So in this case, I can continue an example of this one. Yeah. Yeah. Look at here. New research findings. Yeah. Okay. Rainbow coloring and rainbow anti-magic coloring. Naturally, we have this condition because rainbow anti-magic coloring has more restriction or condition, more constraint, of course, a little bit harder than the original rainbow, then of course the rainbow anti-magic connection, yeah, is bigger than or equal than rainbow connection itself. I already published this one in International Journal of Mathematics and Mathematical Science. We also having a publication of a journal in quartile Q1. Yeah, we have a lower bound. Yeah. So if we have that's lower bound, then exactly I can say here the theorem. Yeah. For Tn's greater than equal 3 and element n, then RAC of fan and fan of order n is 4 and n. 4 is if n equal 3 and if n greater than equal 4. So there is a what piecewise condition. Sometimes we couldn't say for all type of order. Sometimes we should distinguish between a specific order and the other order. Yeah, look at this one. For fan, we have n equal 3. We have n greater than equal 4. For wheel, we have different cases, but for bipartite graph, we have all cases for m, and then we have also a graph operation between complete of order 1 plus star, and we also having this one. Yeah, so that's why what I have already sent to you. Hopefully Sharifa also share my slide presentation as well to your student. So the strategy, how to prove it, the strategy how to prove the lemma follows this strategy. Okay.
See the Prof already shared the slide in the group, our group, WhatsApp. And
Yeah.
we got it. Just I want to ask that
Would you make it loader, please?
a few results here you already published actually. Can we have the full paper?
Article.
Yeah, definitely. I will send you in the group my full paper to you, and then it's already published. We have so many papers of my student result, but the thing that you consider for the publication in a journal, also I'll give it to you, and then you can consider. Yeah. Okay.
Because we need to understand how to prove the
Yes.
theorem, lemma, and so on.
Yeah, definitely. Yeah, okay. So let me have a plan for your student to have an effective collaboration. Why do your student try for having a very simple and specific graph, yeah, from the beginnings, assigning label to vertices, and also observe the etuate, yeah, and then try to find out the bijection. And in next meeting, maybe the student who are already obtained some specific graph whether it is already published or not, no problem. Yeah. Because it is just an exercise, you should present in front of us. What do you think? Or share in a group. Yeah. And then I make it some correction or whatever. And then I will understand that you already understand. Yeah. What do you think? Yeah. So if not, then sometimes it is very hard in this turn that I already, now that you understood. Yeah. What do you think in the next method?
I agree, Prof.
Okay. Okay. Yeah. Okay. Alhamdulillah. Yeah. Alhamdulillah. Yeah. Okay. So any question?
Any question?
If not, I just add one more technique or strategy how to do a calculation of the order or the HV. Yeah. Okay. Let me show you. Yeah. Okay. At the beginning, this meeting, I'm talking about path. Now we are talking about cycle or ladder, for example. Yeah, this is a cycle. Yeah. So, of course, you will have a lot of vertices in a circle. So when you have x1, x2, x3 up to xn, yes, it is cycle having a vertex set xi, the same one, I, yeah, n. But for h, what do you think? Okay.
And
Yeah, this is important. Yeah. Again, the same xi plus 1. But what do you think here? N or n minus 1?
N.
N minus 1. Yeah, because if you have n's, then it will be xn plus 1. But in fact, it is not xn to xn plus 1. Yeah, n minus 1. But what about this one? With this domain, it does not cover this h. Then we need to add union xn x1. So that's the h set. Now we are understand, yeah, that the what? This one is h. Yeah, is n minus 1 because this one and this one calculated once, then we have n. That's a difference. Yeah, understand? Yeah.
Okay.
Okay. Just having a what exercise to do cardinality counting. Yeah. Because it is important when you develop a function in a lemma or theorem. Okay, that's it. Now, for example, again, what about this one? Yeah. Now you have a vertex here. We have a vertex here. Now you couldn't say, or you couldn't give a notation like this one. Yeah. 9. No, this is wrong. Yeah. Understand? Yeah. How do we give a notation? Need to consider in which part of vertex sets having a same or similar properties. Of course, upper side and bottom side. So now you should say x1, x2, x3, x4, x5 up to xn. Then y1, y2, y3, y4, y5. Ya. Brian kemana, Brian? yn. Yeah. Okay. Understand? So, in the future, your student will be having a problem dealing with the cardinality counting. Since the graph is quite complex, then need to have notation first. After having a label and rainbow anti-magic coloring, then you should deal with the notation. Different people, different notation that they have. Okay, no problem. But if they have wrong representation of notation, then the formula and the lemma will be mistake or will be not good. Yeah. So need to have this one. Look at this one here. If you have this notation, what is a vertex set? Ayo, siapa yang bisa?
N plus M.
No.
Cannot.
No, vertex set.
Oh, vertex set. Oh, vertex set. Alright.
Yeah, xi, comma, yi. Yeah. And
N.
yeah. So cardinality n plus n, because xi consider having n vertices, for yi consider having n vertices. So it is 2n. What do you think? Yeah. Now, what about h? H is a little bit complex now. Can you see? What about h? H set.
X.
Yeah.
I.
Yeah. Xi.
X.
I plus 1. Yeah.
Xi plus 1.
Okay. Then, if you have the same domain, just put together in the one vertex set. If it is different, then you put union. No problem. Yeah. What is that? Why one?
We can combine. We didn't need to put union, Prof. The union.
I don't think so. If you combine together, what about this part?
Okay.
Yeah. Yeah. So we need to combine only y1, yy plus 1. Here you have y and minus 1. Understand? Yeah. And then you should put union. What is the union one? Union x1, y1 mean xi, yi. This one, yeah, up to n. Yeah, understand? Yeah. Okay. Okay, now, what is the cardinality of H?
Cardinality of H.
Yeah, just this one, n minus 1,
Minus 1 plus.
but twice. Yeah.
Yeah, plus n minus 1
Plus
again.
n minus 1 because we have this one and we have this one. Yeah. And
Plus
what about
n
this one?
plus n.
N. Yeah. So you have
3n
3n
minus 2.
minus. Yeah. Understand? Yeah. So just check it. Check it. This one, how many ages they have? Yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. They have 16 ages. What is n? 1, 2, 3, 4, 5, 6. N is 6. Yeah. Yeah. So actually n is 6. Yeah. So n is 6. So for this case, we have 3 times 6 minus 2, then it is 16. Yeah. Understand? Yeah. Yeah. Okay.
Natural number. Any natural number. And is natural.
Do you have a question?
Itu
Mungkin yang lain ada pertanyaan?
Tolerantly they're trying to process, try to get.
Yeah, okay. Yeah. I believe it is important to have the experience. Okay, this one, yeah? Yeah, okay. Ya, coba. Oke. Ya, sila cari notasi dari itu, graf itu, ya. We have a center of a graph. Yeah.
For vertex set and edge set.
Yeah.
Is it for edge set?
Both of them. Vertex set, edge set. Yeah.
Okay.
Let me give you just a graph, pictures from those. Yeah. Because in this one we have a labels of a graph. Okay. Yeah. Okay, this one, this picture actually. Yeah, okay. Then we have the center. Then we have this one. Yeah. So this one called Jahangir graph. Yeah. It is Jahangir graph.
Jahangir.
Yeah. So please, so you can see in the middle is center. Okay. And then you have the what? The rings. Yeah. Yeah. You can say X1, X2, X3. Yeah. x4, x5, up to xn. Yeah, understand? What is V? C, comma.
O, C.
Yeah, this is C, comma.
X, Y.
X,
I,
I.
X,
Yeah,
I, and
I up to N. Yeah. So cardinality is N plus 1. Yeah.
Star. One,
So what about H?
H. H. Oh my God.
What about H?
X, I.
XI
With
to
C.
C.
Then
Then
I between 1 and
what do you mean by between?
I between I 1.
I is equal,
Oh, I equal to.
sorry, element of what?
Oh, yeah.
Odd.
Uh,
Yeah. Yeah. So, okay, if you want to see this one, okay,
2 and tadi.
yeah, I and, but N is odd.
Mm.
What do you think? Yeah, yeah, odd. 1 C, 3 C, 5 C, 7 C. Yeah, understand?
Mm.
Okay. Then union xi plus 1, but this one n minus 1. What do you think?
X.
Yeah. Okay. This one.
With I plus Y. Okay.
Okay.
All right.
Got it? Got it?
Yeah.
Union again. What do you say?
Union.
Union.
Let's see. Union XI X plus Y. X.
What? This one still left. The one's left is this one.
Because X.
Yeah. Yeah. What that?
X and XY.
Yeah. X and x1. That's it. So what is H? Cardinality. And yeah.
Plus and minus
No,
1.
no. And because only odd.
So 2 and 2 and plus 1.
So you can consider the natural number, but you just take it, the odd one. What is the number? Only odd. So if you consider 1 up till 10, what is the odd one? Of course,
10 plus 1.
10 divided by 2 is 5. Yeah. 1, 3, 5, 7, 9. Yeah. So if it is 11, what is the? This one is a little bit. Question mark. Yeah. Yeah.
Prof, let us give us exercise this one.
Yeah. Okay.
In group.
Understand. Agree. Okay.
Yeah.
Okay. I believe it's Sharifa finished for today's meeting, and then the rest of our what discussion is a task for for you, yeah, for the student actually, yeah. So hopefully, yeah, okay, yeah, okay.
minus 1.
Yeah.
Expand X1.
Okay. So it is enough for today. Sharifah, cukup hari ini?
Ya cukup, Prof.
Ya. Ya, kita lanjut untuk pertemuan berikutnya. Brian.
So, Prof. David.
Ya.
So, next week, maybe the student, FIP student will present what they get from
Okay.
our
Agree. Very good. Yeah. Okay. So, do we have we got already WhatsApp group for the student?
Yes. For rainbow coloring.
Rainbow Antimagic. Okay. So, are there a student there?
If I in this group.
Already, yeah. Okay.
Yes.
Thank you very much. Yeah. So I can now I'll them then if we already in the group. Yeah. Okay. So also there is other lecturers apart from you in this group as well.
Yes, totally free.
Okay. Yeah. Okay. Thank you very much. We pray to Allah. Hopefully, we can have a good collaboration. Yeah. So, and then we will. Maybe I will visit your university in the short time, and then I will teach your student as well. No problem. Yeah. So you after you come to Indonesia, of course. Yeah. Okay. Let me finish. Inshallah. We meet again next week in the same time. And
Yes,
Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, Prof.
Thank you.
Oh.